Hey there, and welcome to This Explainer. Today, we're diving into something kind of mind-bending, the fascinating and honestly sometimes baffling friction between cold, perfect mathematics and wildly unpredictable human behavior. You know, we usually think of math as the ultimate truth, right? But the second we try to apply that rigid mathematical logic to actual human interactions, things get really weird really fast. We're going to look at why humans consistently deviate from equilibrium and why our failure to be perfectly logical might actually be the very superpower that keeps society functioning. So, let's kick things off with a pretty simple question. If there's a mathematically guaranteed way to win a game, or, say, maximize your own personal benefit in a negotiation, why do we almost never play it? Seriously, if a supercomputer tells you exactly how to act to get the absolute most money or the best outcome, why does the average human being instinctively choose a completely different path? And more importantly, and this is the real kicker, why does choosing that mathematically wrong path so often lead to us actually winning in the grand scheme of things?
Well, to really grasp why we have this bizarre deviation from logic, we first need to set our baseline of perfection. In game theory, this is known as the Nash equilibrium. Named after the brilliant mathematician John Nash, this concept assumes a state where every single player flawlessly calculates the best response to everyone else. If everyone is acting perfectly rationally in a Nash equilibrium, literally no one has any incentive to change their strategy. Why? Because they're already doing the absolute best they can, given what everyone else is doing. It's basically the absolute pinnacle of logical self-interest.
Now, you've probably heard of the famous prisoner's dilemma, right? It brilliantly illustrates what happens when we apply that ruthless logic. Two people are arrested, and they can either cooperate with each other by staying silent or defect by betraying the other person. If we are perfectly rational calculators, looking only at the potential outcomes, mathematically we should always choose to defect. No matter what the other person decides to do, defecting minimizes our potential losses. It is, without a doubt, the mathematically dominant strategy.
But here is where the whole thing kind of falls apart. When researchers actually put real human beings in these scenarios, empirical studies show our behavior wildly deviates from that classical prediction. Classical game theory predicts early defection and perfect robotic rationality. But behavioral game theory, which looks at what we actually do in the real world, shows sustained cooperation, even in highly competitive environments. We don't always betray each other, we collaborate, we trust, and this completely breaks the classical models.
Section 1. The Centipede Game Paradox. Life and Death in the ER. Okay, let's ditch the abstract theory for a second and step right into a real high-stakes environment, the emergency room. This is a place where rapid, cooperative actions are absolutely essential for survival. We can actually model these complex physician-nurse dynamics using something called the centipede game. Imagine a sequence of decisions where medical professionals take turns, deciding whether to cooperate for cumulative patient rewards or act independently, essentially defecting, for an immediate personal gain, like maybe saving time or avoiding liability. Every time they pass that decision back and forth and choose to collaborate, the overall payoff for the patient and the hospital increases.
Now think about this. If those doctors and nurses acted like perfect, cold mathematical calculators, classical backward induction predicts a genuinely terrifying outcome. They would look ahead to the very end of their shift, realize someone down the line might drop the ball, and they would defect early just to maximize their own personal payoffs. The pure math literally says that if you know a collaboration has an endpoint, you should pull out immediately to protect yourself.
So here's the million-dollar question. If bailing out early is the strictly rational, mathematically sound move to protect yourself, why do these professionals almost never do it? I mean, why do we see emergency rooms functioning at all? Instead of turning on each other, they overwhelmingly choose collaboration. They don't act like hyper-rational robots, and honestly, thank goodness they don't. But how in the world do we explain this mathematically?
Section 2. The Math of Human Trust.
Well, the answer to our ER paradox actually lies in a hidden variable that the classical math totally missed, and that's trust. For decades, economists treated trust like this fuzzy, unquantifiable emotion. But recent research has changed the game by mapping trust into a logistic probability function. It shows that trust isn't static, and it definitely isn't binary. It evolves over time, following an S-curve. The math actually incorporates a trust cap, which is the maximum trust an institution allows, along with a sensitivity metric based on experience and an inflection point, like when a team finally just clicks after training together. Trust grows slowly, accelerates rapidly, and then levels off. And honestly, when you crunch the numbers on this, the results are pretty staggering.
Let's say you apply this trust function to a 10-stage emergency room interaction between a doctor and a nurse. The probability of cooperation absolutely skyrockets. It starts at a super bleak 9.5% at stage 1, but as they interact and that trust builds, the probability jumps all the way up to 74% by stage 10.
What this basically proves is that trust isn't just some warm feeling. It literally, mathematically alters the expected utility of the game. It shifts the entire strategic equilibrium towards sustained cooperation. Because the humans involved are factoring in their growing trust, the payout for collaborating actually becomes mathematically higher than the payout for defecting. Our human deviation from pure logic ends up creating a totally new, much better math.
Section 3. Biases and Bounded Minds.
But hey, trust isn't the only reason we veer away from perfect equilibrium. A big part of it is that our brains just aren't wired to process the universe like a supercomputer. Unlike the identical, flawlessly calculating agents you see in theoretical models, like mean field games, real humans have what's called bounded rationality. We operate with biased information structures, which is a fancy way of saying we don't know everything. We have wildly differing risk tolerances. We use psychological shortcuts or heuristics to make snap decisions. And we rely on subjective, often totally non-rational predictions of the future. Let's face it, we are messy. And actually, scratch that, it's more like this messiness is a feature, not a bug. You see, calculating a flawless Nash equilibrium out in the complex real world means solving what mathematicians call an infinitely complex master equation. It demands that you know everyone's strategy and that everyone knows you know it on and on forever. That computational cost is simply inaccessible to the human brain. We literally just don't have the processing power to be perfectly rational in a complex society.
Which brings us to Section 4, Teaching AI to Deviate.
Now you're probably thinking, okay, but couldn't artificial intelligence finally solve this? Since, AI has the raw computing power to flawlessly execute these equilibrium strategies. Well, when researchers train naive AI systems to perfectly optimize for Nash equilibria, without any of our messy human-like biases or trust functions, the AI basically turns into a sociopath. Research highlights that these perfectly rational algorithms converge on the absolute worst possible outcomes in social dilemmas. They essentially learn to always defect. Because the AI is purely logical, it assumes everyone else is a threat, and it's perfectly willing to burn the whole system to the ground just to protect itself.
So, for AI to actually survive and succeed in our human ecosystems, computer scientists are realizing something pretty wild. We literally have to teach AI to deviate from perfect mathematical equilibrium exactly like we do. We have to build in aligned safety filters to foster a pro-social bias. We're having to program AI to care about fairness and mutual cooperation, intentionally suppressing its urge for strict game-theoretic dominance. To make AI play nice, we actually have to make it a little bit more irrational.
So I want to leave you with this final thought to ponder. We've just seen how our capacity to trust, our mental shortcuts, and our pro-social biases are exactly what let us survive the emergency room and build a cooperative, functioning society. If true success in this world requires us to actively reject perfect mathematical strategy, then maybe human irrationality isn't a flaw at all. Perhaps our unique ability to deviate from equilibrium is actually our greatest evolutionary advantage. Thanks for joining me for this explainer.